Okay, this is gonna be a big old chapter 23. Yep, chapter 23. Let's just go through this homework. Here we go. And that's just what it looks like. Okay. So we have E equals 5I minus 3 minus 3 y squared plus 4j. And we gotta use good old Gauss law. So let's open up the PowerPoint and let's look at it then, right? Or I did just make a piece of paper. Yes. All right. Gauss's law. Well, let's see. Flux. Not a swear word, YouTube. I think it's just gonna be EA. We have E. So flux equals E dot A, but it's really EA cosine theta. And it's asking. Yeah, it's asking what the flux is. Okay. So all we need to do is find the area now. And the area of a, what is this? Just as a rectangle? Or are we supposed to just know? A cube. So all equal sides. And we know the distance is 2 meter. 2 meter I hat, 2 meter J hat. Here you have the cube. It's going to be 2 squared. 4 meter. That's of just one face. Because we're asked what are the faces. So it's just a square. So the top face now. Let's see. Top face is going to be. The flux is always going to be perpendicular or 90 degrees from the surface. So if it's the top, then we know that it's going to just be entirely I hat, right? So then for the top, it's going to be 5 I hat times 4 meters. That's EA. And then cosine 90 is 1. So it should just be that. That's 20 I hat. Y. 20 y squared. No, it won't be that simple. J hat. Well, no, but what, shouldn't it be that simple? No, no, it's not gonna be 5. It's x direction. We're looking for -3 y squared. We know that y is gonna be 2. It's gonna be 4 because it's 2 squared. So it's gonna be 8 times 4 because that's the area, which is, oh boy. -3 times 8 times 4. Getting -96. And let's see if I'm right. Yep, okay, we're right. And now the bottom. And the bottom's going to be -3 times 8 times 4. Oh, might be -8. Let's see. Well, no, no, no. Y squared. 0? Is it 0? No. So y squared, is it from this point to this point is 2. And this is bottom to top. But bottom to bottom is 0, not 2. Or is it just asking for y in general, not y to any one point or the other? So y is going to always be 2 no matter what. So then that should be 8. So then where's the difference here? It'd be negative. It shouldn't be negative. Y. Well, let's see if it was -2. -2 squared plus 4. That'd be 0. That's what I mean. And if that's 0, then everything in that is 0. But it can't be -96 again. And we just did the top face. Bottom face is the same. Same area. And same E. Why isn't that the same? Is it negative flux? Cosine -90, which is -1, would be times -4. It would just make it a positive. Something's up. Something's different. And I'm just assuming it's got to be the y value. But if y is 0, then it's -3 times 0. And it's just the area of 4. And that's not right either. Wait, I got it. Because y is 0, then it's just -3 times 4 times 4. Which is going to be 48. Well, negative 48, but if I just type in 48 should be the answer. Yep. And then it's asking left face. So now this one's going to be 5 I hat times 4. That should be as simple as that is. 5 times 4 is, what is that, 20? But it's going to be negative, no, wait. Yeah, negative 20. Yep. On the right side, it doesn't ask for it, but the right side is going to be so top, bottom, left, and right, back. It doesn't ask for the front face. Okay, so we've taken it that way, and back, it's going to be just Z. So it's going to be K hat. So what's K? How does K hat mess with I hat and J hat? I'd like to just call it 0. But I don't know why. Well, answer is 0, but I don't know why. I'm assuming it has something to do with maybe it's K and J cancel. And the back face is along 0x. So yeah, if K and J cancel, and it's the back face, means it's along x equals 0, right? Equals 0. That's just my theory. And now the net. Now the left and right cancel. So it's just going to be negative 96 plus 48. I'm assuming the front and back don't cancel. Are we even asked what the front face is? Nope. So yeah, negative 96 plus 48. I'm getting negative 48. And 0 for the back face. Yep, everything's right. Awesome. Whoa. No, did it again. I've never done it before, and then I do it twice. Okay. The electric field just above the surface of the charged drum photocopying machine. Dang, is this stupid? It's the inkjet thing, isn't it? Well, charged drum. Drums. It's the things like this. Yeah, you hit it here with a drumstick. Got it. Electric field just above the surface of a charged drum. We know E. equals 2.2 times 10 to the 5th. What's the surface charge density? Surface charge density here is, boy, that's going to be charge over volume. We can find the volume equation for the drum. But we don't know the charge. And we know, boy, E equals QD, right? No, P equals QD. Goodness. Surface charge density. Well, E equals what? We don't know R, so we can't use KQ over R squared. Well, let's see. Q enclosed over epsilon 0, we can't use that. We don't know Q enclosed. Dang you, notes. Do I actually have to look at the notes? These things are so slow. Boy, did I already go through all of them though? All the notes? All of the lights? All of the lights? Boy, I almost think I did. Equals, no, because I don't got that one. Oh boy. E equals Q over 4 pi epsilon 0. Which is just K, KQR squared. It's just that all over again. E 4 pi R squared. I don't have R. I don't have R. E equals charge. That's for a sheet. For a cylinder. Oh, that one requires R. This is looking eerily close to the drum that I made, though. Lambda 2 pi epsilon 0 R. Is that what we're finding is R? No, they just want the charge density. I'd like to be able to use that equation. It looks like there's a drum right there. Gaussian surface, non-conducting sheet. Let's try to use this equation. I don't know. It's the only one that looks like it works. E equals the charge density over 2. It's 3. 2 epsilon 0. So we know these. So can we write it in terms of that? Charge density equals E times 2 epsilon 0. That seems easy. Epsilon 0 is a constant, which is, boy, it's not K. Epsilon 0 is 8.85 times 10 to the negative 12th. So twice that. Becomes 0.77 times 10 to the negative 11th. I'm just going to multiply this times E. Times 2.2 times 10 to the 5th. I'm getting the charge density is 3.894 times 10 to the negative 6th. Does it look right? .84 e negative 6. 89. What's wrong? Let me try it again. 3.894 e to the negative 6. Shazah! No, it doesn't like it. Yeah, what's wrong? 2.2 times 10 to the 5th times 2 epsilon 0. It's got to be darn close. It's got to be darn close. Maybe it's a similar equation. Oh, what am I? What's it? Oh, what? Is this what we're looking for? Okay. They're saying, so close. Well, actually, I don't need to erase all of it. I only need to erase that. It says here in the notes later E equals surface charge over epsilon 0. So why don't I just do that? Now I'm getting the surface charge equals 1.947 times 10 to the negative 6. See how that looks similar? I told you. I probably just used a very similar looking formula. 1.947 e to the negative 6. Okay, those two were awesome. Those two, this is going good. Those two went great. Charge, linear density. Okay. We can start writing. Whoa, too far. Linear density 4.5 nanocoulombs, which becomes 4.5 times 10 to the negative 6 coulomb. No, wait. Nano times 10 to the negative 9th coulomb, I believe. Over a rod. So, rod. Lambda equals Q over L, right? And I do not like the electric field. Dang it, they are asking for the electric field. We also have radius inner and radius outer. And this is going to be 6 centimeters, which is 0.06 meters. And this is 15 centimeters, which is 0.15 meters. Okay. I want to know what's the magnetic field. Is the magnitude of the electric field 15 centimeters from the axis of the shell? Boy. I have an equation, but I'm not sure how to use it. Okay. dq or dx. I don't think we have to integrate this. I really don't. Hello, notes, my old friend. Cylinder, that's close to a rod, but I think we have a rod and ring problem. A wire. It's a sphere thing. I mean, that's pretty close. A wire and a rod. What is even the difference? This just has just an outer radius. They're not finding the electric field, are they? No. Hmm. I don't think it says anything about rods. How the heck did I? How the heck did I get anything to do with a rod through any of this? Because now we're right back in the beginning. Well, Gauss's law. Gauss's law. And it's gonna be over a. It's gonna have to be over one of these things, right? We have an inner and an outer. So, is it just E radius inner, E radius outer? Inner and outer. Oh boy. Let's try it. E equals. Made over 2 pi epsilon 0 Ri. Inner would be inner minus outer, inner plus outer, outer minus inner. Out, take away the inside. It would have to be R0 minus 2 pi epsilon 0 Ri. And since I'm saying that this is what E net equals, we can probably set them equal to each other. 2 pi or 0 equals 2 pi Ri, and then lambdas, and then all of those two cross out, and we're left with 1 over R0 equals 1 over Ri. Cross multiply, it's going to be Ri equals R0. Wait a second, that doesn't make sense. Why is it always like that with me? What am I getting? 0.6 equals 0.15? Am I looking for the ratio? Clearly not. Okay. I'm overcomplicating a very simple thing. All right. It's just going to be 1 over RO minus 1 over RI equals E net. So 1 over 0.15 minus 1 over 0.06. I'm getting negative 10. Negative 10. Is it even close? It's not even. It's not even nearly. Oh, wait. Linear density would just cancel out, wouldn't it? What if we do the whole thing? What if we actually just do the whole entire thing and not just 1 over nonsense? I wonder. I just wonder. Would it be the same thing? Am I wasting my time? 4.5 times 10 to the negative 9. 2 pi times 8.85 times 10 to the, what was it, negative 12. And now we're going to multiply that times 0.06, and we're going to multiply the other one times 0.15. Okay. I'm going to try outer minus inner and inner minus outer. Okay, just kidding me. Is it 809? I'd be sick if it was. Ah, it's not. So why isn't it? Outer divided by inner? I don't know. I hate just throwing stuff at the wall. Definitely not outer divided by inner. It's definitely outer minus inner. It's gotta be. Maybe maybe it is inner minus outer. Well, I guess now we take a look inside and see what's missing. Oh, is it just am I overthinking it? Is it just RO? Could be straight up. Hold on. If that's true, then it should be 539.5. Oh, by golly, it is. It's not looking for E net. It's just looking for E on the outside, on the surface. It's just for what the surface charge density is on the inner surface. Oh boy, last question just talked about surface charge density. Surface charge density is E. Surface charge density equals E times epsilon 0. So we know E outer, but does it want to know outer and inner? Okay. Now that's 0.06 times 8.85 times 10 to the negative 12. Is it 1 point? Let's see. For the inner, 1.19 e to the negative 8. Oh boy, what's wrong with it? Negative. Okay, got it. And then it would be outer times E, and that is 4.77 e to the negative 9. Okay, so yeah, to do that, you just take E0 and then E outer, E inner equals lambda over 2 pi epsilon 0 Ri, and this one is 539.5, and this one is 1348.7, and then just multiply it by epsilon 0, multiply it by epsilon 0, and then yeah, get 1.19 times 10 to the negative 8th negative for surface charge inner, and then for outer, I think it's surface charge, yeah. There's outer, you get 4.77 times 10 to the negative 9th. Wicked. Okay, just a very, very slight misunderstanding in my brain of how things work. Okay. A non-conducting solid cylinder with a radius r equals 3.3 centimeters, which is actually 0.033 meters of a non-uniform with a charge density. This is a volume density then. Yeah. D equals A r squared. A is a function. I'm going to draw better A. 2.6 microcoulombs or meters times fifth Goodness me, microcoulombs. So this is going to be 2.6 times 10 to the negative fifth coulomb per meter. Meter pentad. Hate that. I hate all of that. Oh my gosh. And I'm going to guess that this conversion's wrong. I just did it very simply. I didn't think too hard about it, and I don't have the capacity to think too hard about it. What is the magnitude of the electric field? Well, flux equals E dot A. We've got A. And we can find that E. What's E's relationship to this? Because I know E with surface charge. But I don't know E with anything else. Hello, notes. Hello, hello. EV over, okay. Gosh dang, I don't want to do actual math. Okay. Let me just write out what I'm understanding here. With all of that, of course, this is for spherical geometry. What they say, Gauss law of a cylinder. I'm just going to do Gauss law of a cylinder and then work from there. Maybe it's the wrong way of doing it, but they say E equals lambda 2 pi epsilon 0 r. Now we know that r is involved with the density because we got A. We don't know the density. We can get charge in terms of density by just rewriting this. Wait, R. We need surface charge. That's linear charge density. We have volume charge density. Q over L. Lambda equals Q over L. And equals Q over V. Oh my goodness. So we don't know L. We don't know V. This is where I wish I just had the right equation. No, because this should be the equation we use. We just don't know that. But there's an equation. I have But it's to do with a sphere, not a cylinder. This is the one I have for a cylinder. Oh, wait. This has non-uniform. Oh, no. I know what I must do. Non-uniform. Non-uniform means math. It means math. Ah. Q enclosed is the integral this dv, which equals 1, 2, 3. I don't even remember what it is. Do we ever actually break it down? From 0 to infinity pi. Well, they're all just 0 and 0. This is 2 pi of this here sine theta dr d theta d phi. That's of a Gaussian sphere. That's a sphere. I'm looking for a non-uniform surface. But of other things. Non-uniform. Yeah, give me the... How do you do non-uniform stuff? Notes. Maybe you guys should see the notes, but then you guys are going to see what I'm doing with. I'm clicking on slide 42, and it's not giving me slide 42. I'm clicking it. Can you... Whoa! The mouse doesn't go that far. Oh my gosh. Give me slide 42. Okay. Now, is this... It's going to be a non-uniform. Okay. 6 minutes left. I'm going to see how they do this. I know that 2 of them are already solved. Okay. So it's just 2 pi and 2? 4 pi? Is it always 4 pi out front and then it's just 1 0 to r? So I'm thinking that this would... well, I know that it would... How did that happen? No. Where's the original? Oh my gosh, how did any of this happen? Give me back the brush. It was you, wasn't it? Yeesh. But maybe like a size 2. Whoa, not quite you. Oh my gosh, what brush did I have? What's the standard one? This one? Size 2. Oh boy. Oh boy. What happened? How did this even... Where's the normal one? think that one's the normal one, right? Maybe this one? That one looks good. It was this one. Yes! Winning. Winning! Okay. I will want to watch a tutorial on this one because I'm not understanding the concept too well, and I don't want to just dive right completely in without knowing what I'm doing. So I think I'm gonna watch or look up a video for this one. No physics ninja? Dang. Let me get to see if my suspicion is correct. If it's going to be a triple integral with just like a 4 pi out in front. There is integration happening. So this is what's going to happen when we're done with this. I'm going to take my break early because I have to go to the bathroom, so might as well. And then we will come back and do this. All right, let's get to watching this video. No! Now I have to pause though. Just kidding, I'm not pausing the video. In part A of the question, we have to calculate electric at a distance r equals 10 meters. Notice that lowercase. That's going to be what we've done already on a cylindrical Gaussian surface, so that red that shape. Figure out how much charge inside of that charge is. That's going to be our first. That Gaussian, in order to determine the amount of, imagine taking that Gaussian cylinder, dividing it up. We're going to go ahead and draw these cylindrical very. It's kind of hard to describe, but imagine you are going to want to figure out the play of here, and then sort of unfold. If we did that, we end up angular. So we unfolded that, and then there would be the length of the dimension. This dimension. We have a bit of our shell. Try to show that the dimension these two arrows. Very, very that away from you into. Remember that we're looking at the amount of now that charge is only the charge is the volume. More and more of those. Take those out. And inside of r squared r that. I'm just going to integrate relatively towards integration. One to the going to plug in bounds. Your upper bound is r, so you're plugging that 4r, 5 times r to the 4, and then you plug the lower bound in. Lower bound is 0, so throw in r right. Whole expression. And subtract off. So this is going to be the total amount of charge inside. Now that we have the amount of charge. Well, that didn't really. It was usually pretty good. Okay, yeah, they just used Gauss's law. Am I overthinking it? Okay. So Goose's law. See, that's not quite what they had though, is it? For Gauss's law. Maybe they did. So they're getting a DV here, weren't they? Oh, hold on. I think that's properly. No, that's flux of a surface. Gauss's law. No, that is Gauss's law. Yeah. dA. Ah, yep, that's it right there. Not ADA. Just redraw the whole darn thing. And what is the Q enclosed? This is where we have to know. So they say it's 0 to R, volume charge density derived. Maybe I'll go watch that video from the Western New York man. Or what about this video?
charge over what? And this is going to be the surface area of the Gaussian area that we're going to create. And that is going to help us. So density of this is equal to charge divided by volume, right? So let's try to figure out the volume of what we have inside. And the volume is, if you think of kind of here's a cylinder, and obviously we're going to have the circumference at the top multiplied by but it's also going to be a lot. When we go from 0 all the way to 0. So integrate from 0 to radius, 3 pi r. And that's what we're going to use for the bottom. So we can say that Q equals QV. We can substitute P in for that. And Q is equal to area squared. There's going to be integral on volume, so we're going to go from r. There's 1r there.
Okay, sorry, I was a bit distracted.
And honestly, we're going to have the circumference at the top multiplied by u1. But it's also going to be a lot of times. So we go from 0 all the way to 0. So integrate from 0 to radius, 3 pi r.
Okay. So what from there? We got V. We're solving for Q. I don't really get why we're solving for Q. Is that Q charged, the charge enclosed?
So we can say that Q equals V. We can substitute P into that. And get that Q is equal to A squared. And then there's going to be an integral on volume, so we're going to go through to r. There's 1r there, and then we get 2r. We pull out all the constants, so it's just going to be A, L, 2r, and 2r. So that's just going to integrate pretty easily down to A equals, let's say, 1 to the 4, and then just going to be that's what we're going to plug in here. What's the Gaussian area at this point? It's going to be the imaginary area. And it's going to be the same R we're using here. So times 2 pi r. The area is equals A, L, R4 divided by 2x. And this will be that side. So this will cancel. And this will cancel. And this will become 3. So we get the final answer here is A 1/3 divided by 4. This is for part 1. So the solution to this one is just going to be E equals 0.319. That's going to be the solution for the first problem. And the second time, we're going to be using a very similar type of stuff. But this time, let's realize that when you integrate this stuff, here equals a power 5 part of 4. That radius is.
Boy, this is very mesmerizing. I'm trying to follow along with this. Very good video.
Welcome to my channel. Please look at the first chapter 22. Chapter 22 is about the Gaussian law. So we look at it until as we have a long solid non this tells us the charge is uniformly distributed inside this cylindrical object. And this object is radius, length, density given.
No, we don't have a uniform volume charge density. Would be this. I'm gonna go back and try to watch what was he saying.
If you haven't done so yet, pause the video, reread it. Conducting as a radius centimeters, labeled that radius. In part A of the question, we have to calculate the electric field distance of r equals centimeters. Notice that lowercase r, uppercase, feel that here. That's going to be our lowercase r. We're trying to figure out the electric distance. What we've done already is we've drawn a cylindrical red cylinder that's kind of dotted there or dashed. That is our Gaussian circle. We want it in the shape of a cylinder because that shape coincides with the shape of solids. The great challenge of this question is to actually figure out how much charge is enclosed inside of that. How much charge is located in this. That's going to be our first task. Talk about that Gaussian cylinder is solid. To determine the amount of charge within it, I actually want to imagine taking that Gaussian cylinder, dividing it up into a bunch of shells, a bunch of cylindrical. I'm going to go ahead and draw one of the shells right now. One of these cylindrical, it's got a very teeny tiny thickness, as you can imagine that you are going to want to figure out the volume of the cylinder. One way of appreciating the volume of a cylindrical shell is to imagine longitudinally. We cut a line here and then sort of unfold it. If we did that, we would end up with rectangular shape. So go ahead and draw that.
This is what I'm not getting. This is getting just really into the weeds. But maybe he needs to.
This circumference here becomes this dimension right here. Of course, circumference is 2 pi r. And then we have a small bit of our shell. We tried to trim that. That thickness would be the dimension between these two arrowheads. Very, very tiny thickness. So if we draw that here, draw as a tiny dimension pointing away from you into your computer screen. That is, because it's so tiny, we're going to call that a r, or its calculus dimension. Use differential notation to represent that. So that tiny. Now, looking at this shape on the left side of your screen, that's essentially a rectangular prism. And the volume of a rectangular prism would just be sort of its length times its height. So basically multiplying the three dimensions together, you by r multiplied by L multiplied by D. That's going to be the volume of this cylindrical shell. And we don't want just the volume, we want the charge. Let's move on to the charge. And we're going to actually call that charge dq. The reason we're saying dq is it's because it's a amount of charge. Remember, this shell that we're looking at is thickness, so the amount of charge on it would also be
Now, that charge is going to equal volume charge density times the volume of our solution. The question gave us the volume charge density expression A times R squared. Basically, that just means charge. So we're going to actually make a little substitution here.
I go back. I zoned out.
DDR. Now, looking at this shape on the left side of your screen, that's essentially a rectangular prism. And the volume of a rectangular prism would just be sort of its length times. So basically multiplying the three dimensions together, you would get by R multiplied by L multiplied by D. That's going to be the volume of this cylindrical shell. And we don't want just the volume, we want the charge. Let's move on to the charge. And we're going to actually call that charge dq. The reason we're saying dq is it's because it's a tiny amount of charge. Remember, this shell that we're looking at is a very tiny. So the amount of charge on it would also be tiny. Now, that charge is going to equal.
Zoned out again.
Represent that. That tiny. Now, looking at this shape on the left side of your screen, that's essentially a rectangular prism. And the volume of a rectangular prism would just be sort of its length times. So basically multiplying the three dimensions together, you would get R multiplied by L multiplied by D. That's going to be the volume of this cylindrical shell. And we don't want just the volume, we want the charge. Let's move on to the charge. And we're going to actually call that charge dq. The reason we're saying dq is it's because it's a amount of charge. Remember, this shell that we're looking at is a. So the amount of charge on it would also be. Now, that charge is going to equal volume charge density times the volume of our.
Dang it.
And we're going to have 2 pi r multiplied by L multiplied by D. That's going to be the volume of this cylindrical shell. And we don't want just the volume, we want the charge. Let's move on to the charge. And we're going to actually call that charge dq. The reason we're saying dq is it's because it's a amount of charge. Remember, this shell that we're looking at. So the amount of charge on it would also be. Now, that charge is going to equal volume charge density times the volume of our solution. The question gave us the volume charge density expression A times R squared. Basically, that just means charge. So we're going to actually do a little substitution here. The rho R squared, and the volume as noted was pi R dr. So that's the amount of charge on that single Gaussian cylindrical shell. Now imagine you take a bunch of these shells and kind of nest them one inside the other. That you can build up the Gaussian cylinder that we drew earlier. So again, we're taking just the shell and then adding it more and more of those shells together, sort of nested within each other, to give us that solid surface. And so to get the total charge on that Gaussian cylinder, for the bounds, we're on a radius of 0 all the way up to the our Gaussian. The left side becomes the charge here. The right side, of course, we're going to be pulling out some A, I, and the length of our.
Yeah, these people took very, very different directions.
And then inside with R squared, I'm just going to integrate relatively straightforward integration. You're just using basic power rules. Add 1 to the power to the R to the 4th, divide by that power. And you're going to plug in bounds. Your upper bound is R, so you're plugging that 4R at 2 pi times R to the 4, and then you plug the lower bound in. Lower bound is 0, so you plug 0 in R right here. That whole expression, when we subtract off the 0. So this is going to be the total amount of charge inside our Gaussian A. Now that we have the total amount of charge enclosed by the cylinder, we turn to Gauss's law. Gauss's law tells us that the total electric flux through the Gaussian surface
Goodness me, we haven't actually gotten to the integration or anything funny. That's so freaking it's so funny.
is taking place to the sides of it. It is a long cylinder. If it wasn't, there would technically be flux coming out of the left end neck and also out of the right end. But because it's long cylinder, flux through the left and right end to be all we really do need to consider the electric flux going to the sides of the galaxy. We have these electric field vectors away from the Gaussian surface. That is because the charge inside the galaxy is positive. Point electric field away from. And in addition, we have these so-called dA vectors. It's a little weird, but you might want to imagine that there's a little square Gaussian surface. What you do is you point your dA vector away from the side of it. Always point away from the inside of the Gaussian surface. And what you can see is that the electric, the dA are pointing in the same direction. That would be true whether we do it on the top or on the bottom. Because the bottom of the dA vector and the E vector are direction. So that means that the angle between them is 0 degrees. That's important because you can rewrite the dot product as the magnitude of the electric field, the magnitude n times the cosine of theta. But since the angle between them is 0, 1, in addition, the electric field is going to have a constant value no matter where we are on our. That is because we are located a radial distance r no matter where we're standing. So if I'm standing right here, located this r, I'm located r from the center, is uniform throughout. So the electric field outside of our Gaussian cylinder, and because the electric field is uniform or constant, we can factor that out. Now we're just left with the integral of dA. Of course, the integral of dA would just be the sum of the areas of those little black squares. Go back and look at the black squares all over our Gaussian cylinder. Add up the area. That would just be the area of the side of. Maybe we all know that the area of the side of the cylinder from geometry background equal to 2 pi r times. So the area of the sides of n is going to be 2 pi r.
I had no hope at doing this off the dome.
Fill that in. Yeah. Okay, now the fun part is that we get to cancel some terms here. Let's be careful. Look, we've got a 2 pi on each side, so those are going to cancel. We've got an L on each side, so those are going to cancel. And then we have an R, one here, R to the there. So we're going to be able to cancel one factor of R cubed. So if we simplify by canceling, see, electric field E is going to equal, let's see, we have a 2 and A R cubed over 4, and then that's all over epsilon. We can further simplify because 2 over 4, that's going to be. And then this 2 right here. Oh, actually cancel that 2. Yeah, I'm sorry, that 2 right there. We actually still have a 4, but that 4. At long last, we have our expression of the field. And now it's just a matter of plugging in the data. We have the radius of our Gaussian 3 centimeters. That, of course, meters. We have the value of A. It was given, but I don't remember what it was. So A was 2.5 microcoulombs per meters to the fifth. Now that's 2.5 micro. So we got to make sure we do 2.5 times 10 to the minus. And then the value of epsilon naught is. We've listed those values. Let's plug them into our electric field. And when you simplify that, you should get approximately 1.
Wow, okay, yeah. I'm gonna have to work on that problem. Definitely. Half of this session. Gosh dang. Okay, I'm gonna give myself just a few minutes to try this. But I really should be in bed. I keep doing this to myself. Okay. this nonsense out of here. This is good. Yeah, Q enclosed. What did he have? Q equals EV. And volume he had was 2 pi r l dr. So now we've got Q. Well, I can just do this. AR squared times 2 pi r l dr. Now if that's dr, this is dq. Is this where you put the integral? And if so, why?
Yeah, so we're going to actually make a little substitution here. Integrate. For the balance, we're integrating.
Nope, he didn't put it where I was hoping, or where it makes sense. Let's put it here. The bounds are 0 to r. So he can take a 2 pi l out. This used to be r squared to the 0 and r. R to be r cubed. Because there's an r here and there's 2 r's right there. So this is going to be a 2 pi l r fourth over 4. What you could say actually is, you could say it's just half. Half a pi lr the fourth. But I think he left this as is. Because this would be negative 0 and then it's out to the r. Now we've got Q enclosed. E can go out front here. Which just leaves us with the integration of dA. Equals a 2 pi lr fourth over 4 over epsilon 0. Is that the right? What's this guy got? But A is
Of dA. Of course, the integral of dA would just be the sum of the areas of those little black squares. Go back and look at those little black squares all over our Gaussian cylinder.
some of the areas is just, what is that? What's the formula here?
Equal to 2 pi r times. So the area of the sides again is going to be 2 pi r. Now for Q, we developed an expression for that earlier. We have that 2 pi a r times 4. So we're going to take that expression, fill that in our equation here. Now, okay, now the fun part is that we get to terms here. Be careful, look, you've got a 2 pi on each side, so those
Yeah.
cancel.
So 2 pi l this becomes the third. Now I have E equals A R the third over 4 epsilon 0. And this is going to be 4 epsilon 0. Keep, change, flip. You can multiply both sides by 4, which should give you 4 epsilon 0. And then I guess you just put it right back. Or remember that dividing by division is multiplication. Something stupid like that. Something really stupid. He says just push it down. So I trust him. And now, what do we just plug in R? A equals, yeah, 0.6 times 10 to the negative 6. I wrote negative fifth. No, it's fixed. Times 0.023 squared, right? Cubed. All over 4 times 8.85 times 10 to the 12th. Oh boy, I'm getting a terribly, terribly, terribly low number. Which is wrong. Which is very, very, very wrong. What?
You got an FB centimeters.
I'm getting exactly what he's getting.
That's where the charge is located. So here, now earlier we integrated, this becomes the total enclosed charge. That's the area of that red cylinder. The red cylinder. There it is. Is that integrate from TSE? That is the correct answer. Per meters to the fifth. Now that's 2.5 micro. So we got to make sure we do 2.5 times 10 to the minus 6. That'll put it in. And then the value of epsilon naught is known. So we listed those values. Let's plug them into our electric.
Oh, I did times 10 to the 12th.
When you simplify that, certainly 1 point.
Okay. I'm getting 0.893. Oh, snap. That was actually, it was actually correct. And now let's do it for 4-3 instead of 2-3. I'm getting 5.839, so 5.84. Mm-hmm. What's magnitude of the electric field at 4.3? What's the difference?
The electric field is newtons per coulomb. That is the correct answer to the question. But that's just part A. In part B, we're asked to calculate the electric field distance of representing that scenario. So there is the black cylinder, and now the Gaussian surface is still cylindrical, but because its radius is larger than the cylinder's radius, you can see the Gaussian cylinder kind of encloses the entire structure, cylinder, the non-conducting. Now we still need to calculate the net charge inside that red gap surface before. Here's the expression that we developed earlier. Now earlier we integrated from 0 to the radius of our line. We have to integrate from 0 to the radius of the black cylinder. That's because, let's not forget that the charge that's enclosed by the red cylinder, all of that charge actually resides on the black charge is located. So if you're trying to figure out, well, gee, how much charge is in that black cylinder, then you need to use the radius of that charge is residing on the cylinder. There are no charges here, for example. That's you wouldn't want to use the radius of the cylinder because that little space, that little white space down here, doesn't enclose anything. Careful there. You want to make sure you're using the black cylinder. Now, if you integrate and plug in, have something similar. We would have 2 pi a L, have R to the 4. Again, we're going to be plugging in bounds from 0 to capital R. When you plug capital R in there, this becomes capital R to the 4th. You plug in 0, which is out. This becomes the total enclosed charge. Now we can go back and
How did he do any of that?
that we developed earlier. Now earlier we integrated from 0 to the radius of our Gaussian. We have to integrate from 0 to the radius of the black cylinder. That's because, let's not forget that the charge that's enclosed by the red cylinder, all of that charge resides on the black cylinder. That's where the charge is located. So if you're trying to figure out, well, gee, how much charge is on that black cylinder, then you need to use the radius of that. Charge is actually residing on that cylinder. There are no charges here, for example, in white space. You wouldn't want to use the radius of the cylinder because that little space, that little white space down here, doesn't enclose anything. Careful there. You want to make sure you're using the radius of the black cylinder. Now, if we integrate and plug in, we would have something similar. We would have 2 pi a L. We're going to have R to the 4. But again,
There's going to be an R on the outside?
From 0 to capital R. You plug capital R in R to the 4th, plug in 0, which is out, becomes the total enclosed charge. Now we can go back and use our expression we developed for the electric Gauss's law. So there it is. It's Gauss's law. We have the electric field multiplied by the area of our Gaussian surface. Now that's a key. Area of the Gaussian surface is the red cylinder. So if you're going to be doing the area of the Gaussian area of that red cylinder, the red cylinder, lowercase. Be very cautious there to use lowercase r rather than uppercase. And then on the right side, you've got the total enclosed charge. A moment ago divided by that. We can begin simplifying. It looks like we have a I and a pi that can cancel, L and the L can cancel. Let's go ahead and rewrite our expression. And then if we divide both sides by little r, put on the left side, and right side, right there. So again, reminder, little r was the radius of the black cylinder, which was centimeters, 4 meters, and r was the radius of our Gaussian surface. That was bigger. That's 5 centimeters. Go ahead and plug in the values. When we simplify that, we should get an electric field.
Why is his R not on top?
So be very cautious there to use lowercase r rather than uppercase. And then on the right side, you've got the total enclosed. A moment ago divided by that. We can begin simplifying. It looks like we have a that can cancel, I and a pi that can cancel, and the L and the L can cancel. Let's go ahead and rewrite that. And then if we divide both sides by little r, then on the left side, and then right side, right there. So again, reminder, capital R was the radius of the black cylinder, which was centimeters, 0.04 meters, and little r was the radius of our Gaussian surface. That was bigger. That's 5 centimeters. Go ahead and plug in the known values. When when we simplify that, we should get an electric field of approximately 3.6 meters per coulomb. That is the correct answer. .05 meters.
Okay, now I'm getting E2 equals 7.6. 7.6. No. .02. Yeah, okay. I just had big R and little r switched. Okay, I'm absolutely beat. What's that, 2 hours? Not bad. They're just about to actually hit the study session. No, it's still about 13 minutes. Okay, what else? So, yep, that's it for today then.